So today what we're going to do, we're going to continue with properties of radicals, but specifically we're going to look at sums. And please remember, when you see the word sum, it means sum or difference, because a difference is just the negative sum. Okay, remember it's adding the opposite, so you're still adding. Okay? Now, the rule is the most important part here. Okay? Treat exactly like variables. Just treat them exactly like variables. That's it. Once you've done that, you're good to go. And you'll see that today. Think of it as if you would treat like variables. Simplify it, and then combine, instead of like terms, combine like radicals. For example, very basic, I know that. Pete, x plus 2x is how many x's?
3x.
Easy, right? So it's the same thing as this. Okay? Again, see how there was an x right here and an x right here? Now I'm putting a radical 3 and a radical 3. What's really in front of this?
Amazing.
1 plus 2 gives me that 3 right there, and you carry over this radical 3. That's it. It's the whole thing for today. If you can remember that, you're good to go. Everything else is just simplified so that you get the same radicand. Clearly you can see, right? Remember how these are like terms? You can add them. These are like radicals, so you can add them. Are these like radicals at first?
No.
They're not, but if we simplify them, they will be. Okay? Simplify root 48, simplify root 75. You're going to get the same radicand, and then you could add the coefficients together, just like we added the 1 here and the 2 here together to give me 3. If I had this, can I do it? X plus 2y? Why not? They're not like variables. So if I had this, can I do it?
No.
Okay, there's nothing you can do there. So these parts, these we cannot do because they're not like variables or not like radicands. Is that easy enough to remember? Okay, so again, we treat radicals the same way we treat variables. Okay, just make sure you have that rule written down. Who wants to step me through part A now that you know the rule? Summer, go for it.
Okay. You can reduce the two radicals.
Good. So what would you reduce 48 into? What would you break it into?
I'm not sure. Like, I don't even hear. I'm sorry.
Okay.
I don't know.
What about the set here? You know what? This is a good point. Because 48 is tough to remember. What would you break 75 into? What number goes into 75? Think about 75 cents. What goes into 75 cents?
25.
Yeah.
To 25 and 3.
So if there's a 3 there, there's got to be a 3 here for this to work, right?
Okay.
So what times 3 gives you 48? That's the real question now. And it's 16, and it happens to be a perfect square. I saw the hands. Thank you, guys. Okay? And that's how I treat these problems. So if you have trouble with one of them, maybe go to the other to give you an indication of what you should use.
Alright.
This becomes?
4
Good.
radical 3 and 5 radical 3.
Which yield how many radical 3s?
7 radical. No, 9 radical.
9 radical 3. Very good. Okay? Easy enough?
Yeah.
That's the whole lesson for today. That's pretty much it. Now, we need to remember that sometimes the simplifications might be tougher than others. That was an easier example. Okay? Yes? No? Maybe so? All right, try the second one on your own, please. Try part B on your own. 5, and ignore the 5 at first. Try and break it down first. So it's 5 times the cube root of 16 minus the cube root of 54. You need to be able to simplify these before you can add and subtract. So that's the practice we're doing here. We're practicing simplifying this now. So again, ignore the 5. Just put the 5 in front. And immediately start by writing in blanks here. Okay, that's what you should see on your paper right now. And that's what you need to fill out. Jules, is that a technique?
Yeah, see, 8 times 7 is 1, 2, 3, 4, 5, 50, and then 3 times 2 is
Interesting. I was wondering what you were doing there.
That's
No, that makes sense, totally. I was just curious. I watched you do that from here. That's really cool.
Yeah, like 25 about it.
Yeah. 8.3 repeating. Who would have thought?
You should get to know that.
Have you seen the 9 tables? The 9 tables with the fingers?
Yeah, what is, someone tried to show me that in 3rd grade, and then I like,
You know what else?
Okay.
like one, like you go to like the 7th and the 9th grade or something. I don't know.
Yeah, 9 times 6 is 54.
Oh, I just figured out.
Put the 6th finger down. Count from here, okay? 1, 2, 3, 4, 5, 6. Drop the 6th finger, 54. 9 times 7, put the 7th finger down, 63. 63.
Oh my god, that makes sense. So cool.
You do this. And then
You do this, cross them, and you go.
You do this.
Ah, yeah, the broken thumb.
Okay, you have this, right?
No, you have to, someone has to do it. What are we doing?
Oh yeah, we do like.
Oh, go to the door! Somebody go to the door, Josh. Go to the door. Somebody go to the door.
Okay, what's gonna happen?
What can I break the 16 into that has a perfect cube involved? Katerina. Thank you, Katerina.
Thank you.
I have an excellent.
Johnny.
27 and 2.
Okay? Again, if you had trouble with this problem, it means you might not have your perfect cubes memorized. We've got 1, 8, 27, 64, 125, and then we can stop there. They go on. But you should know those ones. So why do we do that, John? Why do we use 8 and 27 as our numbers? What does it leave behind?
2.
Yeah. See the common radicand now of 2? It's like a common variable or a like term. So at this point now, we simply write out what we've got. Okay? 5 times 2, everybody?
10.
And then 10 minus 3?
7.
So it's 7 cube root of 2. Okay? Again, 10 is here. This 10 minus 3 gives us the 7 right here.
Use a small bladder.
Dude, big feet, small bladder.
Alright, come on. Next,
You just want to find out what's happening.
part C. 50 over 3 plus 2 over 3. Each under radicals.
It's like a tattoo in the skull.
Tribal dance.
It's like a siege going on.
More than I don't.
It's fine. Somebody's just working on something. Now, first of all, before we start this, Alejandra, did you still have a question on the last one?
No, you answered it. Well, I have another question.
Let's hear it.
Okay. I have a calculator that if you do this thing, if you put radical and then like a number that doesn't have, if that isn't really a square, it gives you the answer, like the number outside of the radical. Is that a way to do it on this?
Is there a way to do it on that calculator?
Yeah.
Not that I know of.
My dad made that calculator was like 10. It can't be better than this one.
I've never heard of it, to be honest. You're saying it breaks down the radical for you.
Yeah, and it gives you the answer.
I don't know, but honestly, if there was, I wouldn't show you, so it doesn't matter.
If I teach myself, can I use it?
As a checking technique, sure, yeah.
No,
You should still show the work.
Get your answer.
Okay, for this kind of a problem now, there's 2 ways to do this. Okay? We could try breaking down the numerator by itself first and adding like terms, or we could also just rationalize the denominator to start. Either way works. Which way do you guys want to take the approach of?
I have a question.
Mm-hmm.
Could you add them because they both have the same denominator?
Well, if you separate them, you can. So you could do this. Ready? You could think of this as okay, which would then become, whoops, like that. That's all you could really do. Okay, but you cannot add the radicands themselves now. Okay? Now, 50, though, can be broken down, can it? Yeah, 50 would be 5 root 2, because it's really 25 and 2. Right? 50 is 25 times 2. So you could go on and say Okay, that's what you could do here. Now, that's one method, but we still haven't gotten an answer. Right now, we'd have 6 root 2 over root 3, and we still have to rationalize the denominator, though, right? Nick? We still have to rationalize that denominator. We do it a lot. That's why I'm making you get up. I know it's not on purpose, but it has to close all the
Do you
way.
know why Chinese custom opening doors is good luck in household?
We have the window open, don't
I have
worry.
an aunt who says that.
So,
But this is not a
6
household.
root 2 over root 3 still needs to be rationalized. So we should multiply by what, Johnny?
Root 3.
Over?
Over what? Over root 3.
Good. Remember, we got to say the whole statement there.
No, but by saying, oh yeah.
If you just say root 3, that just means the numerator, right? So this becomes 6 root 6. Right? We take the root 2 times the root 3 to give us this root 6 right here. Root 3 times root 3 is root 9, which is really just 3. So this simplifies even further to become 2 root 6 as our final answer.
Holy cow.
Yeah, like a flow chart here. I tried to draw arrows so we could see. That's one method to solve this problem. Okay? That's one way. The other way to solve it would be to try to rationalize the denominator immediately of each term.
Is it easier?
Okay? No, really, it's no different. It's not tougher, but it's not easier. It's just another way to do it.
A little shorter.
I'll show you the other way.
So you multiply the 50 by 3 here.
Yeah, you start by, and let's go over it. So you can step us through it, Manor. So we got 50.
Wait, Sean, Excel? Question on the last one.
Uh-huh.
Just before we get to the next one. When you do like radical 3 times radical 3, that just makes it a 3.
Yeah, because it becomes root 9.
Oh, okay.
Right?
Yeah, I was looking at
And you could always do that. When you have a root times a root, the root cancels if it's the same number underneath.
Okay, that makes so much. So like
Okay.
if I did like, if it was like 4
Yeah.
times radical 4.
Well, that's different because 4 is the perfect square. We try 5 to make it easier.
Okay.
Root 5 times root 5 is root 25, gets back to 5. Okay? So, in this method, Mahanor, tell me what you said we would do here. Yeah, very good. Okay? That's the other method to start this problem. To try and rationalize immediately. And this is actually quite simple, this method, I think. It does not matter, though, really, which way you choose. Now, what happens here is we end up getting radical 150 over 3 plus radical 6 over 3. Mike, what does root 50 break up into? Or root 150? 50 and 3, but those aren't perfect squares, yeah. Think it'd be perfect squares? 6. Very good. And you know how you can know that? 50 and 3, if you have 50, you got to double the 3 to get to 6, right? So this breaks into this. And take a look. Notice 6. So there's that 6. If you want to show up again.
666.
Now, root 25 is really what? 5.
Yay. Go George.
5 root 6 over 3 plus root 6 over 3 is 6 root 6 over 3. Simply equaling 2 root 6. Same answer as we had earlier. Okay? To be honest though, I don't know. Is one way easier than the other?
I like the other one better.
No, I think this one.
This makes bigger numbers in this
Yeah,
problem.
that makes bigger numbers.
Yeah.
I'd rather,
So it's up to you to choose.
I'd rather look at this one.
Yeah. So then the first method would be easier then.
You're so rowdy.
Okay? I want to make them a little more complicated. No different, just more complicated.
Oh, this is hard.
The third one is definitely the most complicated for sure. The first one's easy. It's just a matter of remembering your same rules of the distributive property apply. So start, please. Do the first one on your own. That is right. Try the first one on your own, please.
You add square roots.
Jules, I'm
Does
getting
it
there
become
for you.
12?
Yeah, just leave it.
12. Root 12?
Yes, yeah.
Oh, I want to do
The second part would become minus 12 root 12 plus 20 root 18.
I'll give it that.
Insides, insides, outsides, outsides.
Can we take a step back?
Outsides, outsides, insides, insides, multiply. So the 4 by 3, that gives you a 12.
And then you.
6 times 2 is also 12.
Okay, so it's all multiplications, right?
Yes. And then the negative negative, though, becomes what?
Positive.
So that's going to be positive 20 root.
18.
Yes. Very good. Okay, in case you had trouble, that's what the first line should look like. Remember, and I'll use colors here. I'll use colors.
Use the ring. Oh, wait.
Turquoise.
Okay, outsides work together. So that 4 times 3 is what gave me that 12 on the outside, and the 4 times 5 gave me the 20 on the outside. But remember, the negative negative made that a positive 20. And then, oh, this is too close of a color. Let's try orange. This root 6 multiplies by the root 2, and then it also multiplies by the root 3. So 6 times 2 gave me the 12 on the inside. 6 times 3 gave me the 18 on the inside. Okay? It's alright.
Wait, I don't know what to do.
After this, you mean, or no?
I did that, and then I broke them up.
Yeah, break them up.
Stop.
Okay, let's keep going. So this is going to become... You see the 3 left over in the root? John, you see there's a root 3 left over in the first part? It means it's probably going to be a root 3 over there also. Okay?
Well, why didn't you do... Okay. That's interesting. Alright, 'cause I didn't do that. Okay.
Now the issue is this. Yeah, the last part is not going to be a like term, so we're not going to add it. Don't worry about it. Okay? You're not making a mistake if that's what you're wondering right now. We all see that? And I did that on purpose to show you guys that, sometimes problems aren't all going to combine like terms. It's like having x and y in the answer. That's fine. Same idea. So the middle two can combine, or the first two. Let's write them out. What is this going to become? 12 times root 4. What's root 4 really?
2.
So this is going to become 24, right? Twenty minus 24.
So 4 root 3.
Negative. Come on.
Well, that's a command.
Just don't forget that negative. Okay?
This is complicated.
It's not complicated. It's just you have to be very careful and meticulous. There are a lot of steps along the way. Little errors will cause issues. Okay? Can you see? Are we clear on this problem? It's a tough one for sure, but it's something we should be able to do. This is an easy example of an SAT problem. Not easy in the sense that it's easy to do, but this is something that you can definitely see on your SAT. It'll say, simplify the following expression. And you have multiple choice. Your other choices will be all the common errors. Students who add the numbers in the inside when you can't, we have to multiply them. Forgetting a negative sign. Trying to add the 3 and the 2 together at the very end of this problem. And making it like negative, or somebody will make it this. This is not right. Yeah. They'll add the outsides and add the insides, and that'll be a choice. Okay, that is not correct.
What did you get on your math SAT?
You got an 800.
Got an 800? What?
Yeah,
You've asked me this before.
How does that even happen? What did you get on my
650.
And then
There's only one. There's no writing. It's just reading.
was
There's no essay.
Oh, that was before
It was out of 1600 when I took it. It was out of 1600 only. 8 plus 650.
That's 658.
Did you
1450 out of 1600.
Like when you took so it didn't hard at all.
No,
What do you mean?
Like when you took
harder than
Math?
Yeah, like you just found it really easy, right?
English was hard though for me.
Yeah.
I took it 8 times.
Yeah. Yeah,
On the math I always did, but the English I had trouble with.
My brother took the SAT like 3 times, so he could like pick a score from there.
Yeah. The math I got to 800 right away, but the English I actually got 650 the first time. I never went higher. I got a private tutor and everything for English, but
They don't.
well, English is like, for math it can definitely help having a tutor. But English, you either know words or you don't. Like, I mean, there are so many. I didn't study it all on my own. I was a bad student with English. I didn't read books when I love reading now. I love reading. When I was a kid, I didn't read enough, so I didn't have a good vocabulary. And when I took the test, they had analogies on there, and analogies are tough. You guys don't have those anymore. It's really good. It's a good thing. Trust me. We'll talk more about it. Let's finish this though first. I'm a grammar king. Grammar's all rules. I was so good at grammar, and it wasn't on my test.
Oh my god.
I'm a really good proofreader.
Like today, right?
Like really good. I'm not joking. Like I find errors in everything.
But what's such an argument?
That's great. That's great.
I'm really not a good writer in general, but I'm a good proofreader. They're different things. I'm not a real writing person. And social studies, I was okay in it, but like I didn't like it at all.
I hate memorizing dates and stuff like that. I can't.
Let's look at part B.
So,
It's tough, I agree.
Oh my god.
Would you bring the X to the?
I think I'm gonna take the SAT.
Well, let's try and break it down first, right?
Were you the smart, like the smart one of all your brothers?
Yes, he was. Of course he was.
Usually I would start.
My brothers are all very smart.
Of course he was smart.
My older brother got his degree as a gym teacher, actually, but he never used it. Meaning he's not a gym teacher.
Why would you do that?
Right now, he's a bartender. He worked at a bank for a while. He did a lot of things. He's good at numbers and stuff, too. He was able to get a good job there. He does a lot of stuff. He's probably going to become a gym teacher eventually, but he subbed for a while in public school system, which is like the worst thing you can do as a new teacher, because it's like being a sub in a public school is like not fun. You know? Yeah, students give subs a hard time, so he got a bad experience, and he was like, I don't want to teach after going through that. But I was like, it's not like that. Like, you're not going to... But
What do you have to do to get a degree?
Or you go to college.
you go to college for education in phys ed. Yeah. But again, public school is different. Private school is totally
Is he
different.
working for Bacardi? Is he like a show bartender?
He's a bartender.
He's a regular bartender.
No, these guys are like world class.
No, I know. He's a regular, like, yeah. I know, John. How do you know, John?
These guys make 120 grand for like 6 months in Vegas.
That's his life plan.
Break up x cubed, please. Break up x cubed. We need a perfect square on the outside.
Really good idea.
Root X and 4.
Say again?
Root X and 4.
Well, that's x to the fifth. Yeah. Okay, what about x cubed?
X2 and X.
There you go.
Hit the jackpot.
Okay, again, we need perfect squares. So you take out the x squared from the x cubed there. See that? We take out the x to the fourth from the x to the fifth. Which leaves us, take a look, with the same radicand.
Wow.
So we have, ready?
oh, that was cancelled. Right? Because it'll become like X squared.
You're-
See what we have now? Very good. We've got like terms. The root x in the middle is or under the radical is the same. So now what we can do is take 4x squared minus x squared, giving me how many x squareds, Nick? And carrying over the root x. Okay? Again, treat this here, all these parts I'm showing you now, treat them as if they're variables, which they happen to be, but treat them like the rules of variables. Treat this as a coefficient. You have 4x squared minus x squared giving 3x squared. Okay, treat that as if it's a number or a coefficient. Okay? Last problem for the day.
Wait, this is how I do it. So this is, are you going to put this online tonight?
Of course.
About what?
Of course.
Alright.
This is Howard guaranteed.
It's the Mr. Howell guarantee. Alright. Let's see. Pete, help me out with just the first part of part C. You see that y to the fourth there?
Yep.
I got cube root, so I need a perfect cube. So what should I break it into?
Well, it's 4, so well, 2.
That's for square roots. Yes, I would do 2. But I have a cube root. See that?
Or like 1 point something.
It would be if you divided them correct. It would be 1.33. But I want to break the y to the fourth into either one of the options. Either this or this. That's what I could break it into. Which of them has a perfect cube?
The second one. Y to the 2y to the second.
Cube.
Oh, y to the third.
Okay, let's slow down because I want to make sure we're clear. See these here? Manny. See these right here? These are both perfect squares because they're square and they're even. But if I want a perfect cube, because this is a cube root, I use wherever I see a cube now, okay? Or something that has an exponent that's a multiple of 3, okay? So let's make this y to the third and make this y. I caught you off guard there. Sorry, Pete. The second one. A lot more complicated, right? See that? A lot more complicated. So, before I begin to try and rationalize, let's break everything down for the second one. So I'm going to carry over that 5. Now, I've got the cube root of 2y to the 4th over 54. Jules, step me through.
Did we really have to rationalize?
We're going to have to.
Oh, I didn't.
And you got an answer that had like terms?
Yeah.
Without a radical in the denominator? You probably have a radical 2 left in the denominator.
Yeah. Doesn't that like cancel out the radical 2 on top?
It's 2y.
Oh, yeah, sorry, Jules. We don't have to rationalize. Sorry, I jumped the gun there. I saw the 54. Good point. Okay. Jules, step us through what you just said.
Okay, so it becomes 2y and then 2y cubed. I mean y cubed, just y cubed.
So, before that though, show me what you were just saying, or show the class what you were saying about the 2 and the 54.
Oh, because the 54 becomes 27 and 2.
Yeah, see the 2 and the 54? Let me point it out. See the 2 here and the 54 right here? Okay? 2 and 54 reduced to 1 over 27. 27 happens to be, as Jules said, a perfect cube. Okay? So write this as like that, right, Jules? Over 27. Okay? Again, the 2 and the 54 reduced to 27. I was going to actually break up the 54 into 2 and 27, but then the 2's would cancel anyway, so I would have seen that. But that's a very good point that you made there. I like that. Continue, Jules.
And then the y becomes...
No. Oh. Okay. Sorry, continue.
So then it becomes 5y.
Well, left side first. Sorry.
I'm confused.
Continue on the left side first.
Oh, then it becomes 2y over 3.
Good.
And then it's 5y over 3 radicand y.
Let's go through this just so we're all clear as to what happened here, because it looks like sometimes magic. This, the cube root of y cubed becomes y. Okay? The cube root of y cubed becomes y. This y here is still left over under the cube root, so we leave it here. The cube root of 27 is just 3. So we write it as a 3. Okay, so it's 2/3 of y, cube root of y, plus 5/3 of y, cube root of y. The denominator happens to be a common denominator, right? So we can add the numerators. 2y plus 5y times the cube root of y, which gets carried over, all over 3. How can I write this to make it look a little bit different, even though it's the same answer? Alejandro?
Does it matter where you put it? No. You do 7y. Oh, we can put it at the front and then have cube root of y divided by 3.
Oh, okay.
Multiply by that. No. Yeah. Cube root of y.
That's one way to write it. Good. Another way is to write it like this. Okay? So again, thinking of 7y over 3 as the coefficient, we write it this way. Thinking of 7y as the coefficient, we write it this way. Thinking of it as a numerator and denominator, we write it this way. All of which are acceptable. Is this clear? Yes? No?
Maybe.
Maybe? Maybe so?
It could.
I said baby. That's strange.
It'd be very strange. Okay? Your homework. Okay, 1 through 15 odd, 18 through 42 multiples of 3. Lots to practice. Lots of simplification and adding and subtracting like radicals.
No.